160 million suns are colliding with one another in complete darkness. It sounds unbelievable, but there's no other way of describing this pair of supermassive black holes that astronomers discovered in December 2021. The fusion of these two monsters will take place at a record close distance from Earth, just 89 million light years away. Okay, it's not that close, but one day we'll definitely invent faster-than-light spaceships, and then we'll undoubtedly need a star guide map to avoid the most dangerous objects in the universe: black holes. Which ones lie in wait for us right around the corner in near space? Why can a black hole not only suck you up, but also roast you? And where's the lair of the most dangerous gravitational monsters in the universe? What black holes can we encounter right next door? Astronomers recently discovered a binary star in the Telescopium constellation, and it comes with a bonus gift: a third invisible object. That's a black hole 5 times heavier than the Sun, but its unbelievable density makes it just 30 kilometers in diameter. It's not that easy to make your ship fall into this black hole, even if you wanted to. However, scientists are still worried because it literally wanders around in our backyard, just 1,000 light years away from Earth. So let's map this black hole next door, even though it's tiny. A bit farther, 1.5 thousand light years away from our planet, there's another unusual black hole in the Monoceros constellation. Just 10 kilometers in diameter, this tiny object stretches and squashes the neighboring red giant like a soft toy. This black hole is 2.6 times heavier than the star. If we didn't spot this tiny monster, our spacecraft could be overloaded when flying past the red giant. In the interstellar outskirts of our Milky Way, there are dozens of known objects similar to black holes. At the same time, astronomers believe that in our galaxy, there are at least 10 million black holes formed from massive stars. It's challenging to find and map such small objects, but they don't pose any serious threat to space travel anyway. But what if things were different? What if a similar black hole somehow appeared near our planet? Due to super strong gravitational influence, the black hole would begin attracting the Earth towards it, and at the same time slow down the passing of time. For example, if a planet's path to a black hole took only a few minutes, on Earth this would turn into hours, days, or even months or years, depending on the effect of the gravity. We wouldn't know the difference, but if there was an outside observer, they would notice the planet changing rapidly. Perhaps for this person, millions of years of evolution would fly by in just a minute. But it's simply impossible to predict the appearance of a black hole near the Earth. There would be no black disk on the horizon. The sky would not darken. Our planet could be destroyed by a black hole with a radius of only 2 centimeters, or 0.8 of an inch. If we were to encounter such an object one day, our demise would be very sudden. Any black hole has an event horizon near which tidal forces are activated, but their effect is uneven. One side of the Earth would experience more gravity than the opposite. So-called spaghettification would begin. It's quite difficult to imagine this in the example of an entire planet, but it's easy if we talk about a person. If you fell into a black hole feet first, your feet would be more intensely attracted by gravity than your head. They would be stretched first. Even worse, your hands would be pulled a little in the opposite direction. As a result, you would not only stretch out, but also shrink towards your center. At some point, you may realize that you feel strange, but there would be no time to understand what was happening. You'd be stretched out in a matter of seconds. For the Earth, falling into a black hole can be compared only to the apocalypse. You wouldn't be able to twist the Earth with such great force without damaging it. The tidal forces of the gravitational field would turn you, rivers and lakes, forests, and the entire planet into threads of atoms. And then the singularity would split it all down into literally nothing. But how soon this would happen, and if it would happen at all, depends on the mass of the black hole. Which of the world's most famous space monsters is the largest? Our nearest supermassive black hole is located in the Sagittarius constellation, 26,000 light-years away from Earth. There lies the most dangerous object in the Milky Way, a supermassive black hole called Sagittarius A*. For billions of years, this insatiable giant has been swallowing up everything that enters its gravitational field. But in 2014, the gas cloud G2 managed to escape this black hole, and that was quite a shock for scientists. Why has this neat trick made the cloud so famous? In terms of astrophysics, all the odds were against G2, and it simply shouldn't have made it. A black hole's superpower is its ability to pull things and never let them go. Its boundary is called the event horizon. Everything that ever crosses this line, let it be an asteroid, photons, or even an Imperial Star Destroyer, will stay inside the hole forever. When the cloud moved past Sagittarius A*, there were 40 billion kilometers between G2 and the event horizon. That's indeed a lot. For instance, there are roughly 6 billion kilometers between the Sun and Pluto. Can the gravity of a black hole catch an object from such a great distance? It depends on the mass and the size of a black hole. Sagittarius A* weighs as much as 4 million suns, and its diameter almost equals the minimum distance between the Sun and Mercury. If we imagine that a black hole is Magneto, G2 would be an iron coin located 1 kilometer away from him. Magneto could easily summon much larger things. As we see, the universe signed the cloud's death warrant. So, how did G2 outwit the laws of physics? The story began in 2006. A team of astronomers detected the gas cloud G2, situated 6,000 light-years away from us. It was 3 times heavier than Earth and was heading toward the center of the Milky Way. Calculations indicated that the black hole was supposed to pull the cloud and rip it apart in 8 years. But something went wrong. The pictures showed that G2 was approaching the hole at around 10 million kilometers per hour, but then it rounded the hole and started moving away from it at an even higher speed. Scientists called it space failure. Researchers soon noticed that as it was approaching Sagittarius A*, the cloud stretched out in its direction but recovered to the original shape after leaving it behind. What's more, G2 was very hot, and this heat was stimulated from the inside. The answer was obvious. G2 is not a cloud, but a dense atmosphere of a star. That was the star's gravity that saved the cloud from being pulled to the black giant, and that restored its previous shape. Astrophysicists at the University of Cologne, Germany, have made a statement. According to their observations, G2 consists of not just 1, but 3 stars, whose estimated age is 1 million years. As we see, the miracle that saved the gas cloud G2 was the fact that it isn't actually a cloud. But that's nothing compared to giants from distant galaxies. An absolute monster lurks in the Coma Berenices constellation, 300 million light-years away. This black hole in the center of a giant elliptical galaxy has a mass similar to 21 billion suns, and the size of its event horizon, that is, the region of space where the gravitational pull is so strong that even light cannot escape, is 70 billion kilometers. There would be more than enough space for 3 of our solar systems to Pluto's orbit within such a diameter. Just one slight navigational error on our way to this distant galaxy, and our spaceship is destroyed. but an absolute record among the black holes known to science is held by TUN 618 in the Canis Venatici constellation that lies at a distance of more than 10 billion light-years. This object strongly absorbs interstellar gas and has a mass of 66 billion suns and a diameter of 242 billion kilometers. So much room is enough to fit 11 solar systems in a row. And even more so, a gluttonous TUN 618 could be more enormous nowadays, since on Earth we see it the way it used to be 10 billion years ago. Our planet will be affected by the gravitational pull of a supermassive black hole, but it will be much weaker than if the black hole were small. For a while, people wouldn't even notice that the Earth was being consumed by this black monster because the passing of time would slow down. Catastrophic changes wouldn't occur immediately. In the case of an ultramassive black hole, we may even be able to live the rest of our lives out normally inside it. But there is another possibility. Most likely, most of humanity would perish before the Earth crossed the event horizon. Because of the gravitational attraction, the Earth would constantly be shaking. The power of the tremors would only increase. Cities would begin to collapse. The Earth would be covered by tsunamis. Volcanoes would wake up, including those that have been inactive for centuries. Numerous eruptions, the sky covered with ash, landslides, giant faults, fires. It's almost impossible to survive under such conditions. If the Earth collided with a black hole with a mass of 66 billion masses of the Sun, a huge amount of energy would be released. According to scientists, it's about 32 decillion megajoules of energy, or 32 with 33 zeros. This power is equivalent to 500 septillion of the bombs that were dropped on Hiroshima. It's not difficult to imagine the fate of the Earth under such a bombardment. It would simply turn to ash. It's impossible to escape a black hole after crossing the event horizon. Nothing else would remind us of our planet's existence. It would simply disappear from the universe. And by the way, the other planets would also be dragged over the event horizon and cease to exist. Eventually, the black hole would swallow the Sun. Even if the planets survived, it wouldn't be for long. Their orbits would be disrupted, and the result would be rather predictable. What would happen to you personally if you somehow survived all the cataclysms and, together with the planet, found yourself drawn into a black hole? Nothing good, of course. What we know about the interior of black holes comes from Albert Einstein's general theory of relativity. Beyond the event horizon, all laws of physics cease to exist. Space and time are no longer interconnected realities. Inside a black hole, they merge, losing their independence. Scientific publicist Amanda Gefter writes that the moment you reach the event horizon, you seem to freeze in one place. So it would seem to any outside observer. A planet, a person, any object in a black hole would freeze, as if someone has put them on pause. And then, reality would split in two. In one reality, you'd be torn apart along with the planet, or incinerated by the heat of the Hawking radiation near the event horizon. But in another, you would dive into the black hole alive and unharmed. That is, you would be both alive and dead. You can't stay alive and dead at the same time unless you're Schrodinger's cat. But black holes make all the difference. On the one hand, according to the laws of quantum physics, you can't cross the event horizon. You must remain on the outside of the black hole. After all, no information is ever lost forever. But on the other hand, the laws of physics require that you fly through the event horizon alive and unharmed. Otherwise, the general theory of relativity would be violated. So, the only reasonable explanation of what would happen is an instant cloning of the Earth and you. It's a good thing there are no black holes in our solar system so far. After all, in 2011, using the Hubble Orbital Telescope, scientists discovered that black holes can also move. Why should we be afraid of rogue black holes? Well, have you started suffering from trypophobia, a panicky fear of holes yet? No? Well, then keep watching this video. In June 2011, scientists noticed a bright star at a distance of about 20,000 light-years from us. With the help of the Hubble Space Telescope, astronomers had been studying it for 6 years and came across a very strange thing. The star's light became brighter over time, as if there were an invisible lens-like object between it and us, its observers, though that lens had cosmic proportions. Since the lens itself didn't emit any light, but only distorted it, scientists assumed that it was an invisible black hole, somewhere around 7 times the mass of our Sun. But after about 300 days, the lens seemed to disappear. After analyzing the changes in the star's light, the scientists concluded that this black hole didn't stand still. It drifted at a speed of about 45 kilometers per second. But how is this possible? The point is that at the end of the life cycle of a supermassive star, its core collapses under its own weight after its thermonuclear fuel is depleted. That's how a black hole is born. These deliveries are often followed by a powerful energy outburst. It turned out that it can be so huge that it sometimes throws a newborn black hole right out of a star's womb and onto an endless interstellar journey. But it's not just supermassive black holes themselves that are a threat. What are the dangers of the effects they produce? An exceptionally powerful bomb is ticking somewhere in the depths of space. It's going to explode. There's no doubt about that. This collision between two black holes will trigger a shockwave with the force of millions of suns. It'll rock the very fabric of our universe and sweep Earth. On the cosmic scale of things, this will happen in an instant. Astronomers have discovered this blazar bomb only recently, even though they've been looking straight at it for quite a long time. The first similar objects were found in the late 1950s and immediately baffled scientists. They're powerful radio beacons situated in places that seemingly have no stars around. Back then, these objects were called quasi-stellar radio sources, or simply put, quasars. However, researchers soon found even more bizarre space beacons, unbelievably bright quasars that showered telescopes with deadly X-rays and gamma rays. It was only in the 80s that astronomers understood they'd been looking at galactic nuclei with supermassive black holes that devour everything they can reach. The thing is, some quasars give us only a side view. That's why we can detect no more than dim radio waves coming from their heated accretion disk. At the same time, we look at other quasars as if from above, so the black hole's pole and its powerful exhaust jet emitting X-rays and gamma rays are pointed directly at us. These quasars were called blazars. If one of them erupted in the Milky Way's core, our planet would have to wave goodbye to its ozone layer at best and to all life on its surface at worst. But this particular unnamed quasar is very far. It lies 9 billion light-years away from us, and during 30 years of observations, scientists never noticed it was posing any threat. Only in 2021, they finally realized that they had spent decades staring at a huge ticking bomb. What makes this blazar different from any other? Regular blazars are unstable beacons because black holes swallow the matter in unequal amounts. As a result, they flicker erratically, like a glitchy neon sign. However, the light produced by this blazar, located 9 billion years away, ticks every second year, as if a keeper comes and feeds it according to a particular schedule. Too bad it can't be true. In the universe, only pulsars can stick to such precise precise cycles, but their cycles are measured in fractions of a second. Besides, they occur because of tiny neutron stars and not supermassive black holes. As for quasars, astronomers saw one of them tick like that only once. Can you see those rhythmic flashes in the nucleus of the OJ-287 galaxy? That's a black hole with a mass of 100 million suns continually piercing the accretion disk around a monster weighing 18 billion suns. That's the cause of the powerful explosions. Although they're irregular too, sometimes flashes happen once a year, sometimes once a decade. Astronomers believe it happens this way because one black hole moves around the other along a very elongated atypical orbit. So far, that's been the only quasar pair known to science. At first, scientists thought that our blazar bomb was just another pair of that sort. But then they failed to use accretion disk explosions as an explanation for the extraordinarily punctual biennial ticking. So what's going on with this blazar after all? Astronomers went through a long list of versions and eventually came up with an even more surprising theory. Imagine that a very bright lamp is shining right in your face. Only it doesn't stay put. Instead, it moves from side to side on its stand. When the beam hits your eyes, you nearly go blind, but as the lamp turns aside, you no longer feel pain, and your sight is restored. That's pretty similar to the manner of blazar flickering. But what can make a supermassive black hole with a mass of hundreds of millions of suns wander from side to side? This is something that only another supermassive black hole with a similar mass can do. What's more, it has to revolve around its blazar being 100 times closer to it than the OJ-287 pair is to each other. If we place this blazar system on top of our solar system, the central blazar most likely would reach the orbit of Mars, and its partner would end up on the border of the Oort cloud, which means only 2,000 astronomical units away. If you think these two monsters have gotten way too close to each other, you aren't wrong. Scientists have calculated that they've been approaching each other for 100 million years and have already covered 99% of the way leading to the collision. Buckle up, humans. What will happen to Earth after the blazar bomb goes off? Thanks to the LIGO, a highly sensitive laser observatory, we know that a crash between black holes impacts the entire universe. In September 2015, the machine detected gravitational waves triggered by a merger of two black holes. Each of them was as heavy as 30 suns, and when they hit each other, 3 solar masses were released as part of the gravitational shock wave. It passed through Earth and all of us at the speed of light, even though we didn't feel anything. That's because the blast was weak, so space expanded and shrank on a much smaller scale than that of even atoms. This time, the collision between the black holes from the blazar bomb will generate an unprecedentedly strong shockwave. At least 10 million suns will be converted into the energy of gravitational waves. We'll have to face tears in space-time comparable to separate atoms. So, what is a shockwave like this capable of? Perhaps it could stop nuclear reactions in the sun for a moment, or break bonds between atoms and disintegrate our planet. In August 2019, the Virgo interferometer that detects gravitational waves caught one very unusual collision. Here's what it sounded like. That was a black hole swallowing up another much larger object. It happened 770 million light years away from Earth, and it's something we'd never, ever seen before. One thing is clear. That was some remnant of a dead star that existed on the boundary between known neutron stars and black holes, in the place where nothing except a void is supposed to exist. And although this Object X disappeared forever after the collision, it could change the way we perceive the universe. But where did that gap between neutron stars and black holes come from? How extraordinary could Object X actually be? And what objects do stars turn into after they die? Why couldn't Object X evolve from a regular sun-like star? We know that at first, such a star turns into a red giant, and then it sheds its outer layers and becomes a white dwarf. This is a strange body. Its mass can be compared to that of the Sun, but it's hardly bigger than Earth. There are almost no fusion reactions in it, and its dim light is a star's residual heat. As a matter of fact, a white dwarf is a barely flickering corpse. In one of the simulations, NASA scientists tried to place it instead of Object X and saw that the black hole absorbed it with a flash. However, nothing like this happened when that mysterious collision occurred. What's more, white dwarfs cannot be as massive as Object X. The Chandrasekhar limit is the maximum mass of a white dwarf star, and that means there's no way it can be more than 1.4 times heavier than the Sun. But what if, while searching for Object X, we test this theory and make two small white dwarfs crash into each other? That's precisely what happened 7,000 light-years away from Earth, in the constellation of Cassiopeia. A couple of two white dwarfs produced a bright and very exotic zombie star. Some astronomers compared it with Frankenstein's monster. But eventually, we'll see that the Chandrasekhar limit isn't just a saying, as gravity will compress the stellar corpse and make it even more extreme. And then it really will begin to look like Object X. But why can't remnants of even larger stars and products emerging after collisions between white dwarfs be our Object X? Ridddle, a blue supergiant star, is 17 times more massive than the Sun, and one day it's going to explode as a supernova. But the stellar corpse it'll turn into will be nothing compared to the size of the star. It'll be just 12 kilometers in diameter, and so it will perfectly fit in Jamaica Bay, New York. This object's gravitational force is so strong that it's crushed even atoms. Every atomic nucleus usually contains protons and neutrons. If extremely compressed, elusive electrons go off their orbits and fuse with protons. As a result, there's nothing left except tightly packed neutrons. Now it makes sense why corpses of massive stars are called neutrons. Given this density, a typical neutron star has a mass in the range of 1.5 to 2 suns. As a rule, when it collides with a black hole, there's no visible explosion. That's why astronomers initially thought that Object X looked like a neutron star. Apart from that, they also studied its gravitational waves and calculated its mass. And here lies the main problem. According to the Tolman-Oppenheimer-Volkov limit, a non-rotating neutron star can't be heavier than 2 suns. Otherwise, gravity will take over and squash it into a black hole. In case this object does rotate fast, we can add 20% more of the solar mass. But our elusive Object X is more than 2 times heavier than the Sun. So what is it? Just a small black hole, case closed. It's a shame, but the tiniest of known black holes is 2 times more massive than Object X, since this mysterious stranger lies on the boundary where, as we tend to think, nothing except a void can exist. Well, maybe a void and some even stranger objects whose characteristics resemble that of Object X the most. However, they are hardly more than a theory. What if we try to add some little extra mass to the neutron star? A supernova explosion is unlikely to leave behind a stellar corpse with such characteristics. So, let's go to our space crime lab and try feeding a typical red dwarf to the neutron star. Keep in mind that a dwarf is around 5 times lighter than the Sun. What do we get? According to the laws of quantum mechanics, the neutron star won't be compressed into a black hole at this point, but will shrink even more and turn into a quark star. The force of its gravity has crushed even its neutrons. Each of them has broken apart into even smaller particles called quarks. It's like cramming a few burritos into one little lunchbox. When snack time comes, you'll have to eat some weird mess. But it's still essential to check what quarks the star is made of, as they can be different and also strange. And then we'll get a strange star. And yes, it's a scientific term, although astronomers strongly doubt that such unusual corpses can emerge after supernova explosions. Strange stars have probably formed shortly after the Big Bang and are still there today. Does our Object X belong to them? According to one of the theories, due to their unique features, quark or strange stars can be 2.5 times heavier than the Sun. Now, that's closer to what we're looking for, but let's not leave it halfway through and consider even the oddest of suspects. Could Object X be an exotic star with the most unusual characteristics and mass? The best way to get one of them is to make a neutron star swallow up a small white dwarf. As a result, we'll have an electroweak star whose mass is very close to that of Object X. At first glance, it looks like a neutron star, but its core resists being compressed into a black hole through the so-called electroweak burning. And it gets energy from those very quarks that, under other conditions, produce a quark star. However, it's estimated that an electroweak star can last 10 million years at most, and eventually it'll collapse into a black hole. Although, according to basic principles of quantum gravity, there may be an alternative outcome. This celestial body is very similar to a black hole, but don't let it trick you. You're looking at a Planck star. If a supernova explosion makes energy accumulate in a certain way, the laws of quantum mechanics won't let the stellar corpse become a black hole. At the same time, a Planck star, as well as electroweak and quark ones, turns out to be nearly a perfect candidate for Object X. And finally, here's the last theory, and it gives scientists a splitting headache. Indeed, the black holes that form after supernova explosions can't be lighter than 5 suns, as they immediately absorb a lot of matter emitted by the dying stars. But if some unknown law of physics spoiled the first breakfast in the black hole's life, this also makes it a potential Object X. In fact, all our versions are so bizarre that whatever our stranger really is, it's a breakthrough for astronomy anyway. What black holes had scientists baffled and therefore are particularly dangerous? A new study by Russian researchers Nikolai Gorkovy and Sergei Tulbashev truly shocked the scientific community, since it's so far removed from the standard cosmological model of a single universe. These two astrophysicists have suggested that our universe undergoes countless expansion and contraction cycles, with a novel theory for what is generally called the cyclic or oscillating model. Think lots of big bangs and big crunches. People far from physics and astronomy will think,
well, if I got shrunk down, I'd probably notice that.
The process is a bit difficult to explain, but I'll help you make sense of it all. Because, as it turns out, we can actually witness the next contraction or crunch. These scientists also referred to the possibility of a super-duper massive black hole forming that will eventually consume our entire universe, and that means together with us inside it. How black holes affect the universe. We are often confounded by the fact that just 5% of the Earth's oceans have been explored, but it's nothing compared to what we know, or rather don't know, about dark matter and dark energy. Knowledge of the processes involved with supermassive black holes was enhanced when Gorkovy and Tulbashev took up the issue. These days, there are thought to be as many supermassive black holes as there are large galaxies in the universe, around 2 trillion, with one big black hole at the center of most of them. But exploring them is obviously difficult and problematic. Modern physics knows that 85% of our universe's mass is something unknown, what we call dark matter. And most of the energy is, if you can believe it, also something unknown. Basically, we simply have very little idea of what 95% of our universe is made of. At this point, all we know for sure about dark matter is that it serves as the glue holding together galaxies with its gravitational heft. That's how we discovered it, in fact, because when we look at galaxies, there just isn't enough visible matter, meaning star systems, to hold them together. And what we call dark energy is, we surmise, a mysterious force pushing the universe apart faster and faster everywhere. This situation is so dire that some physicists, out of desperation, have suggested adjusting the law of gravitation at large scales to fit the observations, so that we can exclude dark matter somehow. So, the news that the gain and loss of black holes' mass might be involved with the shrinking of the universe caused somewhat of a hubbub in cosmology circles.
Oh my God.
Most physicists had never thought about such things before. The Hubble Space Telescope has observed a distancing, a moving away of near-Earth objects and stars on the outskirts of our galaxy. With the Hubble's help, we discovered that the universe is expanding at a rate of 74.03 plus or minus 1.42 kilometers per second per megaparsec. So far, for some of you, these are just weird, incomprehensible numbers. But soon, everything will make sense. Stay with me. The thing is that observations from another space telescope called the Planck, which monitors cosmic microwave background radiation, or CMB, gives us completely different data, only 67.66 plus or minus 0.42 kilometers per second per megaparsec of space. The Planck basically looks at things further away, and that means older, further back in time. So it turns out that the rate of expansion of the universe away from us is lower than it is in close proximity. But in fact, if the expansion of the universe was caused by mass loss in the past, then in the very distant past the rate of expansion would clearly be different from the one we see today. But still, what's going on with dark energy? Why is it more powerful in areas closer to us than it is billions of light years away from our galaxy? And even more questionable is the astronomical revolution regarding gravitational waves that took place in 2016. The American Gravitational Wave Detector, called LIGO, received dozens of signals of different statistical significance, more than a dozen of which had a very high credibility level. And almost all of them are gravitational waves caused by the merger of two black holes. So where did so many black holes come from? Evidently, there must be some unexpected source for these formations. Researchers have suggested what might serve as such a source, and it's a phoenix universe. According to this idea, the existing universe underwent many cycles of contraction and expansion. Our cycle is not the first, and most likely not the 100th. It's just one of countless cycles, like many that came before and many that will come after. In the first phase of each cycle, our universe expands, and that's what's happening now. It reaches a peak size, and then in the second phase, it begins to shrink. With this compression or contraction, the distance between black holes gets steadily reduced. And in the final phase of the shrinking cycle, the diameter of the universe becomes not 93 billion light years as it is now, but only about 10 light years. As the black holes merge into one another, their number will be cut in half. Then the total mass of the universe will be reduced by around 5% as the mass is converted to massless gravitational waves. And the remaining black holes can continue merging into one another, and the mass of the universe will continue to be reduced by 5% again and again. Having reached contraction to about 10 light years, with the temperature now 10 billion Kelvin from compression of the CMB, all the atoms of heavy elements decay, Concurrently, the merger of black holes transforms most mass into gravitational waves, and when this transformation reaches a critical threshold, the contraction of the universe stops, and it starts expanding rapidly. This moment in the model of Tulbashev and Gorkavi is interpreted as the Big Bang, the beginning of the next development cycle of the Phoenix universe. You might ask, if our universe is in the process of expanding now, then how can our expanding universe start shrinking? Well, when black holes collide, as mentioned, they emit gravitational waves, contraction. The evolution of the Phoenix universe bears a resemblance to the work of a colossal pendulum. As the pendulum swings up, its kinetic energy transforms into potential energy, and the upward velocity gradually decreases, finally hitting a peak, and then the pendulum swings down again. The universe, as it expands, will turn the energy of gravitational waves into mass until there's so much mass that the expansion is replaced by contraction. But for this process to take place, the universe needs the intervention of dark matter. Will we be able to observe it? Probably. Passing between the Earth and a star from another galaxy, dark globular clusters of dark matter are likely to create a gravitational lens effect, which we could observe. There's a chance that it will be easy to distinguish from other areas of the sky, but this isn't definite. So, will we know when we've entered a black hole? We've already figured out that if something consumes our entire universe, it wouldn't be one hole, it would be the merger of countless black holes. We're often intimidated by the idea that if we enter a black hole, we'll get stretched out like spaghetti, as our feet, for example, get pulled faster than our head if we enter feet first. But that's not necessarily so. Falling into a black hole will make us face spaghettification and death only if the hole is small. We'll be consumed by something mega, uber, super gigantic. With a supermassive black hole, the difference between the effect of tidal forces on your head and your feet will be insignificant. Most likely, entering such an object will be not only painless, but also imperceptible for most of us. Just like you didn't notice that the summer just went by and you didn't have any fun. Astronomers will follow this process carefully. They'll see redshift in distant galaxies gradually fading away. This would mean that the edge of the main black hole is approaching. Then, everything will suddenly change to a blue color. The universe will go from expanding to contracting. Actually, that would be the ultimate sign that we've been consumed by a black hole. So that's it. You won't have to go to the back of the bookcase like in Interstellar. This fact should make you happy. However, the biggest mystery that science can't explain is the galaxy in the Hercules constellation, more than 2.5 billion light-years away. Judging by the evidence of radio emissions, there used to be a black hole that could possibly be even more massive than Ton 618. However, it's not there anymore. Of course, black holes can evaporate, but it's a prolonged process that takes trillions of years. So, what happened to this space monster is just beyond our understanding. The only thing to calm us down is that all these black holes are very far from us. Or not. One theory about mysterious dark matter, the one that makes up most of the mass of the universe, states that black holes are literally everywhere. They're just very small. One day they got stuck in microscopic size, and now they can neither grow nor evaporate. According to this theory, every big city on Earth has at least one micro black hole. Write in the comments in which borough or building of your city such monsters might be hiding. Could it possibly be them going door to door and stealing socks out of our washing machines? Something to think about.